Chapter 2, chemical basis of life. And like I said, this is incredibly important that you grasp grasp these concepts. And if you have any difficulty at all, see me or go to the tutor. I did email his hours and where you can locate him. So you should have that. All right. So let's just go ahead and begin. Everything consists of matter. Anything that has mass, which is basically weight, we're on planet Earth, so weight is just a pull of mass because we have gravitational pull, and so that's going to pull the mass, and that gives us the weight of that particular object. So everything exists of matter, and matter is going to consist of elements. Now, you've got a total of 92 natural elements, which are found on your periodic chart, periodic table of elements. And you'll notice there are more than 92. Some of these are man-made elements, so they have been able to actually produce some in lab, or maybe you did that at home and didn't realize it. Could happen. Maybe. Anyway, so we do need to have that out, and I think that will make your life better, a little easier if we can do that. Okay, so when it comes to the elements that we have, 98%, now the way they've broken this down is to 96% and basically 3.7 or 4% of total percentage of body weight. But the 98% would include what I would refer to as CHNOPS, which is what most people have used in the past. And so that would be, I'll write it up here. Okay, so this is 98%, which is a huge percentage of total body mass. This would stand for carbon, hydrogen, oxygen, nitrogen. We've already talked about oxygen, and phosphorus and sulfur. So anyway, CHNOPS is what most people recognize as 98%. Like I said, I did divide this out a little bit differently. Notice that oxygen is the highest percentage. That's because we have a tremendous amount of water inside the body. And then, of course, going along with that, it would be the hydrogen. Hydrogen is incredibly, incredibly tiny. So the mass on that is very, very low. So when you see that 9.5, it's a little misleading because the mass of that is so very small. It doesn't seem to take up a lot of mass, but there's a tremendous amount of hydrogen. In fact, there is more hydrogen than there is oxygen, but they're going on basically on mass on this particular table. Okay, so we do have carbon, oxygen. I'm looking at the 98%. Hydrogen, nitrogen, calcium, which it's not included in the CHNOPS. And maybe they've changed this chart some. That surprises me. I'm not accustomed to seeing that on this, but the phosphorus definitely on that, and then the sulfur, and then again they put in a potassium, which I'm not accustomed to either, as being in this percentage of the 98%. So maybe the numbers have changed. Certainly over time, information does change. So maybe this CHNOPS is no longer valid. I wasn't aware of this, and I haven't until we're doing this right now, and I'm seeing that is actually a little bit different. So we will go with the table. So we will use the first four as a 96.3. The others would be 7. And in addition to that, there are what we would refer to as the trace elements required incredibly, well, they give you the number, less than 0.01% of human body. You'll see a list there of boron, chromium, cobalt, copper, fluorine. Don't bother to memorize all those trace elements. It is interesting that you will see iron there, and we do have a tremendous amount of iron in our body. I mean, our red blood cells carry iron. That's what oxygen attaches to. Iron is a metal, and all metals attract oxygen. That's what metals are positively charged, all of them, positively charged. And oxygen typically carries with it a negative charge, and we'll be talking about that quite a bit. So the oxygen will attract to that metal. So that's essentially how we carry the oxygen around in our body. The oxygen attaches to the iron, so the oxygen is negative and the iron is positive, and therefore we form iron oxide, which you know better as rust. So that is how we transport it to our cells, because obviously they need that. I'm going to erase that 98%. I'm thinking maybe that is no longer valid, which is interesting to me. I do find that awkward. Yes, ma'am. Well, I would not. And in fact, I would go with this, the first four elements as being 96.3%. Because if we're pulling any test questions, they're coming off a test bank which is produced by book. Probably it's not really produced by them. It's produced by teaching assistants. Professors got together and wrote the book. You have got a number of authors, and then teaching assistants play a role in that, do other things for the book, and that's just, they get graduate credit for doing those things. So they will put together the test bank. Typically, it won't be the professors that do that. You get the graduate assistants to do all those things you don't want to do, which is good. The beauty of being a professor. Absolutely. There are all these people wanting to be professors, and you get them to do all those things you just really don't want to do. So that's slaves, I think they call them. No, I'm sorry. That's probably incorrect altogether. Okay, so when we begin to create bonding, creating a situation where two elements will be held together by an attraction, we then create what is referred to as a compound. And the only way that you have a compound is really you have to have different elements. Like water's a compound. You have H2O. Obviously, you have two hydrogens and one oxygen. If we were to write that, let's see if I'm still on that. All right, so we have H2O. The symbol H, of course, is the chemical symbol for hydrogen. The 2 is referred to as a subscript, meaning it's written below the script line. So if I were writing on a line, that line should go right here, and the 2 should be below the line. I call it subscript. But it only refers to the element to the upper left of that. So there are 2 hydrogens. You could put a 1 below the oxygen. Typically, you don't see that done. If there isn't a number there, you understand there's only 1 atom of that element. So I have 2 hydrogens in 1 element, and that's definitely going to be a compound of in this case, water. So 2 different elements. If you just had, say, oxygen, gas, O2, that's not a compound. You don't have 2 different elements. You have 2 atoms of oxygen, but you don't have a compound. You have to have 2 different elements in order to have a compound. So there is a significant difference. Now, sodium is a metal, and chlorine is a poisonous gas. And obviously, we don't eat metals. I'm not going to go home for lunch and have a plate full of nails, any kind of metal whatsoever. And I'm certainly not going to breathe in a poisonous gas, or hopefully not breathe in poisonous gas. But if those are chemically combined, you create table salt, sodium chloride, And that's something that our bodies absolutely need. It's necessary, where it's required by the body. And so you can see that when you combine elements together, what you end up with is a compound, and that compound has properties completely different than the elements that went in them. So it completely changes, and I find that absolutely amazing. That goes back to what you call emergent properties. You have properties of sodium. It's a metal, certainly not edible. You have properties of chlorine, poisonous gas, certainly not anything you want to consume. But once you bond those two items together, then you create salt, which has properties completely different than the elements that make up that substance. So properties emerge out of that chemical combination, which again are so different than the individual elements themselves. So those properties emerge out of that. Those are emergent properties, which is very unique. And anytime you create a compound, you are creating something that is very, very different than either of the elements that go into it. And I find that very fascinating that does happen. And, you know, that makes me very curious about chemistry, but not so curious that I'm going to go get a diploma in chemistry, because I have taken chemistry, and I didn't find it all that incredibly fascinating for me personally. Now, you may love the topic and the subject, but I was not one of those people. So I admire those people who can study chemistry and just go, oh, that's great fun. Man, what fun. And I went, man, this is not fun. I don't know. If you hadn't been there yet on chemistry, then I hope you're one of those people that go, man, this is fun. That's great. Didn't have that experience. Now, I did take the organic chemistry, and I did tend to like that a lot better. Now, a lot of you are writing. I do hope you understand that this is actually, you know, on your blackboard. So you don't really have to write anything unless it's something that pops out of my mouth, that which is very rare, that you find interesting. Then you might write that down. Other than that, it's probably not necessary. Hopefully, there will be things come out of my mouth that are not in here. I try to eliminate as much of the text as possible on the PowerPoints. I try to take out just as much as I possibly can, and then try to describe those things. You know, there are so many different ways you can describe a term, and so, you know, what a lot of students have gotten used to, and I don't know why this is the way it is, and I think it comes from public school. You're given a term and you're given a definition, and so you memorize the definition to the term. That's not very useful. You're just memorizing a definition that you probably won't remember. But if you understand the term, there's so many different ways to express what that term actually means. Once you understand it, you can make up your own definition, and to the term. And that's the point at which I want you to get to, is to understand the term and not just memorize a definition for it. And I find that not useful at all, personally. So that bothers me. That's why I take out all of that. I don't like it myself. So without iron, we cannot transport oxygen. We've talked about that. That's what the oxygen attaches to, because the iron is a metal and it's positive, and the oxygen typically carries a negative charge on it. Iodine is something that we need. Now that is a trace element. We don't need much of it. In fact, iodine was the very first food additive, which is interesting. Not that you need to know that, but it was the very first food additive. You know, and now when you look at a package of something, you know, I ate a Jimmy Dean sausage biscuit thing this morning with cheese on it. You know, got it from the kiosk downstairs. You know, I'm afraid to even look at the ingredients on that, because my gosh, you know, when you go in there and you see all these extra things listed, it's not just sausage and biscuit. They got a lot of stuff in there, and I don't even want to look it up on Google because I probably would just stay completely away from it. But they're tasty. I'm sure I don't want to know what's in a Taco Villa meat burrito, but by goodness, you know, I like that with extra red sauce and a whole bunch of those little packets, you know, that they design so that when you open them, they blow up on you, you know, and it goes all over you. You're going, oh God, I got to go back to school with all this all over me. But I think those people that make those packages are just like laughing their butts off because they're like, oh, these are all going to explode on these people. This is so funny. So I pointed away from me, let it hit the wall, splatter the wall before it hits me. Yeah, you develop ways of dealing with things. Anyway, iodine, which is a trace element, we don't need much. But here's an individual. If you'll notice below his chin, he has this big, huge knot. That is a thyroid gland. Now, a thyroid gland produces a hormone which is called thyroxine. And thyroxine is a hormone which regulates your metabolic rate, basically, your metabolic rate. So some people are producing more thyroxine and some people are producing less thyroxine. So if you're not making much, you're probably a laid-back individual who just likes to hang out and chill and, you know, hang out on the sofa, you know, watch a few games or, you know, a few television programs, and, you know, you're very relaxed. You know, and then some of us, like myself, are pretty much just pretty high-geared all the time. And I probably make more thyroxine than a lot of people will make. And keep in mind, I am bipolar, so I do take downers, medications, to pull me down, and I take those 3 times a day, and a handful in the morning, a handful midday, and a handful at night. So you'd think I'd be on the floor. Most people would. One time, a friend of mine and I were walking around the UTP park course, and of course I take these meds all the time, and I just gave this individual a half of one pill that I take. Now I take more than one pill, but anyway, a half, because that person was stressing over something and needed to just relax. And I said, well, just take a half of one of these. This thing won't bother you. You know, this individual was wandering off into the pasture, not on the track at all, wandering off into the pasture trying to find bunny rabbits, you know. And I'm going, I'm driving home. Yeah, I will drive home. A half of one of these. Oh, my God. You know, and I take several a day. But, you know, medications affect people differently. But going back to this, this is a goiter, and what that amounts to is this person does not have enough iodine to produce that hormone, which is called thyroxine. And so he cannot produce it because it does require iodine, and he's not getting it. Now, if he were to take iodine, then the goiter would go away, and he would make his thyroxine, and he would feel just fine. So they discovered many, many years ago, and I don't know, certainly we could look it up easily enough. That's the one thing that once we have Google and all the other search engines, you know, we can discover anything we want to discover, and that's very fast. And, you know, we understand. We can find that answer. But whenever they... That's the reason they... We need to have that iodine to produce that hormone, thyroxine. And so you have people that make very little and people who make quite a bit. And then you have some who have hypothyroidism, which means they make and then people who make way too much. And so what they usually do is go in with radioactive iodine, just so that it will kill off part of the thyroid gland, so you're not making as much thyroxine. So some people will make way, way too much, and they're just bouncing off the walls all the time. the amount that they produce. Either that or they will just get thinner and thinner and thinner and thinner and they will die. So that's just what happens there. Anyway, this guy's probably living in some area where he doesn't have medical care, would be my guess. Hopefully they found him some iodine. I bought him a whole case of iodized salt. You can buy it without the iodine in it. I wouldn't recommend it. You need that iodine. You'll see it on the shelf, grocery store shelf. You'll go, well, there it is. I don't know if I need the iodine or not. You do. You need to buy the one with iodine. It's in there for a reason. Okay, so, and each element is consisting of atoms, and you can have different types of atoms, but basically they all have the same chemical characteristics. So basically they're all the same atom. Like if you're looking at on a periodic table, if you look at hydrogen, there's more than just one type of hydrogen, but they all have the same chemical characteristics, physical characteristics, so they're all hydrogen, even though there may be different hydrogens out there. So the element is hydrogen, and then you have really different atoms, and we'll get into that. Okay, so then we have our different pieces of an atom, and of course, if you want to be an atomic scientist, with no desire, I'm doing what I want to do, but if you want to be an atomic scientist, then you would find out very quickly that you have actually several different parts of an atom instead of just these, what they call subatomic particles. Sub means below, like submarine means below the ocean. If I had a submarine in fresh water, I don't know what you'd call it. Marine means salt water, so it wouldn't be a submarine. It'd be a sub-freshwater vessel. Below the fresh water, in the water vessel. I don't know. It'd have a different term. They probably would use the same term, but it would be inaccurate. Anyway, so we do have three different particles. The proton, protons will have a positive charge. One thing that they're not putting in here, and that does need to be put in there, the mass of a proton, it does have a mass. And this down here, one proton, and that's my abbreviation for proton, a P with a plus. It's not in the book. You won't find it. It's not standardized. It's just what I use. One proton has a mass of one atomic mass unit, referred to as AMU. I use AMU a lot. This book is using Dalton, named after the gentleman who came up with that mass, Dalton. So, one Dalton or one atomic mass unit. I like AMU, which is atomic mass unit. I just like that best. One electron, they are so incredibly tiny that we're going to say it's actually 0 atomic mass units. Now that is ridiculous because absolutely if it exists, it has to have some mass. In reality, one electron has a mass of 1 over 1800 AMU, or Dalton. So you have to have 1800 to equal one atomic mass unit. There's no element on your periodic chart there that's going to have anywhere near 1800. In fact, on your periodic table, the one that has the most electrons is the one in the far right-hand corner at the bottom, Lawrencium. It has 103 electrons. So, not very many at all. So what I'm saying is, they don't have, atoms don't have very many electrons, so we just consider that number to be fairly negligible. It's not going to really affect the mass of the weight of an atom. And then the neutrons always have a mass also of 1. And I use an N with like a little degree on it. So that would be 1 atomic mass unit. Or again, you could use Dalton for that if you prefer. They're both correct. All right. So those will be our subatomic particles. that we find within the atom, and we're going to place those here shortly so you'll see where they're located. Okay, now you can see where they're located. If you've got a sphere that's got a positive in it, then the positive charge of a proton. If you have a sphere with a negative in it, then that's the negative of an electron. So in this region of the atom, we have protons and you have neutrons. They don't have any charge, so they didn't put anything in it, positive, negative. There's no charge at all. And then the electrons travel in energy shells. You can have up to 7 energy shells. This is just the first energy shell. It's closest to the nucleus, which is what they call the area where you find the protons and the neutrons. It's not really anything. It's just the area where you find those. The analogy can be used that if you put a golf ball in the middle of say, one of these humongous stadiums where you'd have, say, like football or baseball, the very first energy shell for the electrons would be the very last row of seats, which will be way up there. So you might as well take your little iPad and watch it on the iPad instead of going to the game. What? Little ants down there. I don't know. That would be a whole lot of fun. Okay, so that's kind of interesting that the electrons are that far away from the nucleus, which are the protons and the neutrons. Now keep in mind, each proton would weigh 1 AMU and each neutron would weigh 1 AMU. So the total weight right here is 4 atomic mass units. These don't have a mass, basically. They're very small. We don't consider that mass. So the total weight of this whole atom would be 4 atomic mass units. You've got 2 protons, 2 neutrons. That's the 4 atomic mass units. These, we don't even consider the mass of those at all. So 4 atomic mass units on that. So everything's made out of atoms. And like I said, if you put a ball in the middle of the stadium, in your first shell was the very last stadium row that you have, there's the longest amount of space with an atom. This table is made out of atoms, which means in reality, and this is kind of hard to wrap your head around, maybe it is for me, but there's more space here than there is solid material. There's more space there than solid material. That's true. That is the truth. But you look at it and you go, but it's solid. you can't put your hand through it, it's solid. But there is more space. It's just we can't see that incredibly tiny. We can't see that small. And I love that concept that whatever it is, there's more space in this wall than there is material, than there is mass. Because of, again, the golf ball and first electrons are way out here somewhere. So you've got that huge amount of space. But, you're working with an atom, which is tiny. And obviously we can't see anything that tiny. So, again, the protons, neutrons are in the nucleus. The electrons are in energy shells. The first energy shell has the lowest amount of energy, and the further away from the nucleus you go, the greater amount of energy you have associated with that shell. So first energy shell has a low energy, and then the very last energy shell, which would be the 7th, and you will never work with the 7th. We don't get into atoms that are that huge, but that energy shell would have the greatest amount of energy. And the energy associated with those shells is very important, and we'll talk about that. We'll see that. Okay, now on your periodic table of elements, or chart of elements, what you're working with, you'll see, and let's look at lithium. Lithium is in your very first vertical column, and you'll notice that at the very top of that it says 1A. The vertical columns are called groups. So beside 1A you may want to put group. That's a group. Vertical column is a group. Okay, so lithium then is the second element in group 1A. Now, then you'll see a 2 to the left of lithium. Now, that refers to a horizontal row, so this goes across the page. So lithium, beryllium, then you go to boron, carbon, nitrogen, oxygen, fluorine, and then neon. So that's a vertical column. That would be a period. Period 3 would be, again, a horizontal row. Period 4, period 5, period 6, period 7. So anyway, periods go across in horizontal rows. So if I were to say, all right, look for element in group 2A, period 3, what element would we be looking for? Magnesium. Group 2A, period 3. So where those intersect would be magnesium. So group 2A up and down, horizontal row is a period. So you go group 2A, period 3, you're at magnesium. I don't want to draw that. I'm in group 1A, period 2, so this is lithium. And so we see a 3 here. We see a really small 2 and a 1 here. And then they give you the symbol. And then they give you, it's what happens when you get over 50. You don't, this used to just come right out of my head, but now I have to look. 6.941. Okay. This is the mass. They should be able to put a AMU at the end of it, or Dalton. They don't, but this represents the atomic mass. So that's what they call it, atomic mass. That is the weight of one atom of that element. And that is the average mass. It's just an average. Average. All right, there we go. Worked fairly well. Okay, and the number that you have in the upper left-hand corner, that's referred to as the atomic mass. Atomic mass is actually equal to the number of protons. That never changes per element. All lithiums will always have 3 protons. And now the electrons, because they're in energy shells, remember the protons and the neutrons are in the nucleus, and then you have all those energy shells up to 7. The electrons are found a pretty good distance away from that nucleus. The electrons are easily manipulated. We can move them around. So I can take electrons off of my hair, which I'm always doing this to keep it out of my eyes. Take it off of my hair and put it on my shirt with the cat hair. I've got one cat who loves to just crawl all over me, particularly after I'm dressed for school. I don't know what that's about. And then I can remove my hair and the cat's hair. No, the electrons that I pull from my hair off of the shirt, I can put them on my jeans, and I can remove the electrons that originated from my hair and then went to my shirt and then were on my jeans, and take them off of that, and then I could eat a few of them. I have no idea how many I just ate, but I just took them from my hair, put them on my shirt, put them on my jeans, and then put some into my mouth, which that doesn't hurt anything. So electrons can be manipulated. You can move them about very quickly, not a problem. So the electron number can change, but when you're on the chart, the number of protons will always equal the number of electrons, and that is on the chart. Not in nature, because it does change. Number of electrons do change. I took them off my hair, put them here, took them off here, put them there. You can manipulate the electrons. So they're certainly not static. They can be moved about easily enough. But on the chart, if I have 3 protons, we're going to just naturally assume we have 3 electrons. Not that we can't move them about. We can. All right. So this is an average number right here for atomic mass. So if I were to say, okay, we had one lithium that had a mass of 7 atomic mass units, and all atoms have whole number masses, all of them, all atoms. Have whole number of masses. Okay, so I don't have any on the planet that has a mass of 6.941. That's just an average mass. Most of them must weigh 7 atomic mass units because that's very close to 7. So let's say that I had 9 of them that had a mass of 7 atomic mass units. 1, 2, 3, 4, 5, 6, 7, 8, 9, and one that weighed 6 AMUs. Okay, so that would be, instead of it being 70, this would actually be 69 atomic mass units. All right, so if I have 69 atomic mass units and I wanted to average that, I would divide it by 10 because I have 10 atoms listed, 9 of them being lithiums that have a mass of 7 atomic mass units, one that has a mass of 6 atomic mass units. So we're gonna average that out, and then obviously that's going to be 6.9 atomic mass units. So if they, and I don't know how they came up with that number. Again, we could always find that, but they took supposedly. And again, I have no idea how they did that. But they took all the atoms of lithium on planet Earth and they averaged out the masses of all of them, and the number that they came up with was 6.941. I don't know how they got it, but you can see from that, you just need to round that to the nearest whole number. That will tell you the most common lithium out there. So most lithium will have a mass of 7 atomic mass units. There are some, like this one, that will have a mass that is different than the most common lithium. We typically use the most common, which just round it to the nearest whole number, which would be 7 atomic mass units, and that will be the mass that we will typically use right there for one atom of lithium. Okay, now, so atomic number, mass number. Let's move on from that. Okay, now the atoms that have different masses, they're the same element but have different masses. So it's like lithium. You had so many that weighed 7 atomic mass units. They all have to have a whole number of masses. 7 atomic mass units, and you had one that weighed 6 atomic mass units. They're the same atom, but they have different masses. Those are called isotopes. Same atom with different masses. Okay. So not all atoms of an element have the same mass, which is why when we first started on this, I said, well, you know, you do have all of the atoms of a particular element have the same properties, chemical, physical properties, but they're not going to be exactly identical. And that's what I was referring to would be you do the typical. Okay, and then so we have what are called isotopes. So you have, as an example, here are some isotopes, carbon-12. Now, carbon-12 is the most common. In fact, if you look at carbon, which is in group 4A, period 2. So group going up and down the page, 4A, and then period 2, go across, you're at carbon. Look at the mass, 0.011, which means most carbons on planet Earth weigh 12 atomic mass units. So we're going to look at the most common, that's carbon 12. But there is another one out there called carbon 14, and it's an isotope of carbon. Okay, so carbon 12, if I wanted to do that, if you'll notice your atomic number, which is in the upper right corner, says 6. That means I have 6 protons and I have 6 electrons. Right? Atomic number, upper left-hand corner, 6 protons. And if I have 6 protons on the chart, I will also have 6 electrons. I'm going to put 6 protons in the nucleus. And then out here we'll have, let's just say 6 electrons for the moment. And then I want to know how many neutrons I have. All right. Well, the protons weigh 1 AMU, the neutrons weigh 1 AMU, the electron weight is negligible, but the total mass is 12 atomic mass units. Okay, so 6 plus 6 will give me the 12. So 6 protons and 6 neutrons weigh 12 atomic mass units. The 6, we're not concerned with the mass of the electron. They are very tiny. Again, that would be have to divide that out about 0.0000 whatever. And so we're not concerned with that. That's carbon 12. Carbon 14 will have a different mass. Now, if it's carbon, it has to have 6 protons. How do I know that? Because all atoms of carbon have 6 protons. That atomic number in the upper left-hand corner, which says 6, that tells you how many protons you have, and it's the number of protons that determine the element. Nothing else. Not the number of electrons, because we can manipulate those. Not the number of neutrons, because that can change. That's what isotopes are. But the proton number never, ever changes if it's going to be carbon. They will always have 6 protons. That is very unique. That tells you the element. Not the electrons, not the neutrons, but the protons. So that 6 is very important. That tells you the element. All right, so all carbons have 6 protons. And we'll have 6 electrons out here somewhere, and then, which aren't going to really weigh much of nothing. And then the total weight on this, we're saying, is 14 atomic mass units. That's what that carbon 14 is about. It tells us our mass. So 6 plus what would give me 14? 8. Okay, so 6 plus 8. So you can see the only difference between carbon 12 and carbon 14, they are isotopes. The only difference is the number of neutrons. That's what makes it an isotope. Isotopes are the same atom of the same element, have different numbers of neutrons. That's it. So they're certainly going to weigh differently. Since neutrons have a mass, then they will weigh a little differently. Okay, so and carbon 14 is radioactive. We're a bit young. I could probably pull right out of my head. The half-life of radioactive carbon, which is carbon 14, I am fairly certain it's 5,730 years. I would bet a small sum of money, not a large sum of money, because once you reach the age of 50, things don't pull out as fast as they used to. But that goes for it's true of the brain. Okay, so I think the half-life is 5,730 years, and this is what they call half-life. I'll talk a little bit about that. Half-life means that if I had a chunk and it's all carbon, like coal, you use briquette in your charcoal grill. I don't know, maybe cook with the gas outside. Personally, I like to use mesquite, let it burn down to coal, and then let it get really, really hot because it gets really, really hot, and then cook with that. But you can buy briquettes, and it's just carbon, that's all it is, black carbon. Okay, so if this were all, this entire thing, briquette, was carbon-14, in 5,730 years, half of this would be carbon-14, and the other half of this, I believe, would be nitrogen-14. It would change elements. It would go from carbon to nitrogen. And radioactively date a sample. They say, well, you know, the amount of carbon-14 and dinosaur bone, the proportion is this. Well, let's back in. Okay, now 530 years, 730 years earlier than that, what would be the proportion? And then earlier than that, and earlier than that, and earlier than that. So you kind of back into actually the age of that dinosaur bone. And so they can tell you within a fairly accurate measurement what period of that particular animal, you know, and if they go yesterday, then you'd go, oh my God, they're still here. We just found one. We're not sure where he lives. Anyway, that could be interesting. Like, oh wait, they're still here. I would love that. Dinosaurs still around. Could be fun. All right, so isotopes, the same element, different neutron numbers, therefore they have different masses. That's really what you do. And some of them are radioactive, like I say. They do have half-lives, and therefore the element changes. So we can use those, and they do use those quite a bit. For example, we did talk about carbon dating, which means finding the age of a sample, which they do all the time. Also, they can use that in what they call PET, positron emission tomography. Tomography. There we go. Yeah, that sounds better. Anyway, they inject radioactive materials, and then they can detect from that because it does attach to tissues, and it does give off radioactivity. Then they can actually detect disorders, like in this case, heart disorders, brain disorders, and so forth. So very valuable tool, and they use it quite often. And you can see the difference between a healthy person and Alzheimer's person right there. Okay, now we got the chemical bonding. That's as far as we got to today, but that's cool. That's fine. You've got about 10 minutes, so we'll take a break, and we'll see you in lab. One thing we need to do in lab today, we need to review. You do have a lab test